So we already finished the first unit, sets. We talk about all the basics about sets. I also gave you two problems, I believe, about the sets. They're not particularly hard, but there are a lot of definitions, a lot of concepts that you need to understand, fully understand it in precisely. So start from today, we're going to go to the topic of logic, unit 2, the second unit. So this unit may be a little longer. It will take a little more time. I believe we already learned some parts of logic in undergraduate. We just go through it again, but with more details. We want to talk about all these definitions systematically, because those are present everywhere in mathematics, in pure mathematics. So the first section is statements. Okay, everybody knows what it means by statement, but in mathematics we have to define it precisely, rigorously. So what is a statement? The definition of a statement is a declarative sentence that has a truth value. So this is important. It has a truth value. So how do you know a sentence is a statement or not? It must be. It must have a truth value, either true or false by some standard, not by your opinion. Some facts, based on the facts, it must be true or must be false. Okay, so by declarative sentence, we mean a sentence that makes an assertion. This assertion can in fact be false, as I said. In that case, we say that the sentence is false. Okay, so here are some examples of statements. For example, the number 3 is larger than the number 2. That's a statement. You can tell whether it's true or not. And we know that it's true. Another example, the sun is blue. We all know that's false. The sun is not blue. Okay, so that's some fact. Or the next example, there are exactly 100,000 words in this book. Well, we really don't know how many words in any particular book, but once you specify a book, then this statement is either true or false. It can have exactly 100,000 words or not. So that it has a truth value. It's either true or false. So that is a statement. Or the number 7 is an odd integer. Obviously, that's a fact. So that's true. Birds are mammals. This is also a statement. There's some scientific definitions about the animals. So you can tell. Exactly whether that's true or not. So, so there are a lot of situations that the sentence that do not make statements. Those sentences could be questioned. What is the color of the sky, for example? It's not a statement. It does not have a truth value. It's just a question. It doesn't give you a assertion. You cannot tell this sentence whether it's true or false. No, it's just asking. Or commands solve the equation. That's not the assertion. Again, you cannot tell whether it's true or not. Or opinions. Chocolate ice cream is the best. This is a little confusing, as you might think, this is a kind of statement, but it's not, because it does not have a standard in here. What is the standard? How do you know chocolate ice cream is the best? What's the standard? It really depends on people. Maybe you think chocolate ice cream is the best, but somebody else does not. So that's just an opinion. It does not have a truth value. You cannot tell whether it's true or false based on some objective standard. Well, obviously, words that don't actually form a sensible sentence do not have truth value. Like try apples that's not a sentence even, so it doesn't make sense. In addition, sentences involving variables such as x greater than 2 are not statements because we don't know what the x is. So it could be greater than 2 or not. It does not have a definite truth value unless you know what number x is. Then you can say it is statement. But if you just say it generally, it's not a statement. It's vague. All right. Any questions about the definition of statement? If not, then let's go to the next topic. Compound statements. We can combine several statements to create more complex statements. And there are a bunch of them, or a number of different operations that can be used to combine and modify statements. We'll just talk about this one by one. So the first thing is called a conjunction. So suppose we have two statements, P and Q. What is the conjunction of P and Q? So you just use a notation like intersection between P and Q to mean the conjunction of P and Q, and it gives another statement. So then this conjunction has a definite truth value. So how do you know it's true or how do you know it's false? So we define this conjunction of P and Q to be true when both P and Q are true, and it'll be false if any of P and Q, P or Q is false, or P and Q are both false. So this is like intersection in the set notation. Okay. So it has similar functioning, but since we're not talking about sets, we're talking about the sentences. We cannot use intersection. What does it mean by intersection of two statements? That doesn't make sense. And so that's why we call it a conjunction. But to figure out the value of the conjunction, it's just like you take the intersection of two things. So you just read it as P and Q with this head. Okay, so for example, if we have two segments P and Q, where P is 2 is an even number and Q is an even number, obviously, statement P is true and statement Q is false. So if you try to make the conjunction of P and Q, then it says and, just put the and between the two segments. 2 is an even number and 5 is an even number, and we know that's not right because 5 is not even number, so that's Q is false. So then P and Q must be false. All right. All right, so that's that. The next thing is called the disjunction. It's just like the union of two sets. Since we're talking about statements, we don't say union, but we call disjunction, and we use a V between P and Q. So obviously, we're just following a similar rule with union of two sets. So if P or Q is true, then the union or disjunction of P and Q must be true, or both. And this disjunction will be false only when P and Q are both false. So pretty simple. So just like sets, we say P or Q if we write the disjunction of the two segments. So let's just see one example. The same example, statement P is 2 is even number, and statement Q is 5 is even number. So PVQ or P or Q, if we just translate this symbol, it means 2 is even number, or 5 is even number. We know that's true because P is true. So PVQ must be true. And that's exactly what it says in here. Although Q is false, it doesn't matter. Any questions? So these are pretty simple things that we already learned. The next compound statement is called the negation of a statement. So if P is a statement, then the negation of P is another statement. It's just the opposite of P. Okay. So obviously, if P is true, then the negation of P will be false, and if P is false, then the negation of P will be true. And the notation is just a minus sign, like a minus sign, but it has some, step in here. So just be a little careful about the notation to distinguish between the minus sign in algebra. We're talking about logic. So we have to use different notations. Just like we are using, the head or V, we don't use the same notation as this, union or intersection between the two sets, right? They're rounded, remember when you talk about the union or intersection of sets, the notation is it is some arc opening up or down. Okay, it's not the corner. So the symbol of this, P, you can read it as not P. So if we wish to express the meaningful meaning behind this negation of P, we can say it is not the case that P holds or P is false. And in many cases, it would be safer to say it is not the case that P holds, especially, when P is a non-statement. All right. So let's just look at one example. We have already know, P, the statement P is 2 is an even number, and that's true. So then the negation of P would be statement it's not the case that 2 is an even number, and we know that's false. Or, that essentially means 2 is not an even number. Okay, so that's a false statement. Pretty straight. All right. Sometimes, you even if you don't know the truth value of a statement, you can still make a negation of a statement. So let's negate the statement P, which is T is raining in London. We don't know whether it's raining in London or not, but it has to be true or false. That's a fact. It either raining or not. Okay, so that's a statement. So we still can negate the sentence. So the negation is it's not raining in London. Okay, obviously, it's not the case that it's raining in London. Whatever the way you say it. Yeah, that's pretty straight. All right, the next thing we call it implication or a conditional statement between the two statements. This one will be a little tricky. So we have two statements, P and Q. We can use them to construct a new statement, and we write it P arrow Q. And this new statement or compound statement is true unless P is true and Q is false. What does it mean? It means when P is true, but Q is false, then this whole compound statement doesn't make sense. That's what it means by this implication. P implies Q. So if P is true, then Q has to be true. So then in that case, we say this compound statement is true. But there are some other cases, that this compound statement is true. The only case where this compounded statement is not true or is false is when P is true and Q is false. Okay, that must be false. That's contradictory to the term of implication. So we have some terms for this statement P and statement Q. So in this implication, P implies Q, and the statement P is called the premise and the Q is called the conclusion. All right. So if the premise is true, then the conclusion has to be true. All right. Let's look at some examples how to understand this implication or conditional statements or statement. So in this example, let P the statement 2 is an even number and Q be the statement 5 is an even number. like before, then P implies Q would be the statement. If then, okay, so conditional statement. So if P, then Q. If 2 is an even number, then 5 is an even number. This must be false. And you don't need to think about this very hard. But just use definition. 2 is an even number. That's the same. And P, that's 2, and the 5 is even number. That's Q. That's false. So if P, then Q. Okay, if P is true, then Q is false. That's exactly that situation. So that compound statement must be false. Okay, according to the definition. And if you actually try to, understand this compound statement from the wording, it could be very confusing. Okay, so suppose we have another statement. We just change the rows of P and Q. If we write the Q implies P, then again we just use the word in if then. Okay, so this time Q goes to the front. If 5 is an even number, then 2 is an even number. Obviously, this doesn't make sense, if you just read this whole thing. But if you use the definition of implication, the first statement is false and the second statement is true. And this compound statement is true according to the definition, because the only time when this compound statement is false is the first statement is true and the second statement is false. And that's not the case in here. So the truth value of this compound statement is actually true, since the premise is false, it's not the only case of false by definition. All right. So many students have difficulty with the idea that the statement P implies Q should be true when P is false and Q is true. How is that true? It doesn't make sense. But actually, it can help to think of P implies Q as meaning whenever P is true, Q must also be true. But if P is false, then anything can happen. You see? So if P is false, the first statement is false, then it really doesn't matter whether Q is true or false. Anything can happen. So it has to be true in any case. The last compound statement is called the biconditional. It's just the conditional statement both ways. So the P and QB statements, then the biconditional P equivalent to Q. So this two-sided, two ways arrow means P and Q are equivalent actually. And it is a statement that is true if P and Q have the same truth value and false otherwise. Okay. So, so how do you know this biconditional statement is true? Whenever P and Q have the same truth value, either P and Q both are true, or P and Q are both false, then the conditional statement is true. All right. So we read P if and only if Q. All right. See, so you can see P and Q are have the same, always have the same truth value, if and only if. So they must be both true or both false. We can also think of it as meaning that P is true exactly when Q is true. All right. So this time it does matter, when P is false, Q is true. That'll be false in this biconditional statement. All right. Let's look at more examples. Suppose P statement 2 is an even number and Q is a statement 5 is an even integer. We already talked about that quite a few times. Then P, if and only if Q is a statement, just put the if and only if between those two statements. So that means 2 is an even integer if and only if 5 is an even integer in this fourth statement, because P is true, the first statement is true, and the other statement, Q, is false. Okay. They don't have the same truth value. Once again, you don't have to, read this whole sentence and think about what it means in here, but rather you just use a definition. All right. In the sense that we will see later, P, if and only if Q is the same as saying that P implies Q and Q implies P. All right. We use this kind of argument, extensively in mathematics when we do the proof of a statement. Two equivalent statements, especially when we, mean two statements are equivalent. We use if and only if. All right. Okay. So we have talked about several types of compound statements. We can define the compound statements in a general sense. Just combine all those compound statements and use some generous language or definition. So, so the definition of 3.18 is a logic connective. So a logic connective is an operation that modifies or combines statements into more complex statements. So the four compound statements we already talked about. We have those, and or negation, implication, if and only if. All of those operations, the symbols are logical connectives. It just make a connection between two or more statements, and it just produces a new statement as a whole. And there's some other connectives, So in here in this table, we just summarize definition of those symbols or logical connectives. And in this table, we have statement P as column 1, statement Q has column 2. P, can be either true or false, and Q can be either true or false there. So if you combine P and Q, then you can make 4 combinations in here. For example, P true, Q true, P true, QF or false, or P false, Q true, P false, Q false. Okay, so that's all the combinations of statements Q and P and Q. And then if you just remember all the compound statements we just discussed the 5 types of logic connectives, if you like. So we have a row for each possible combination of truth values for P and Q. All right. Each row, okay. It's just the possible combination of truth values P and Q. And we have the columns of negation of P, P and Q, P or Q, P implies Q or implication of P and Q, or P if and only if Q. And each row, the entries in each row indicate the truth value of the statement at the top of the column. Okay. So, for example, if both P and Q are true, then the negation of P will be false, and P and Q will be true. P or Q will be true. P implies Q will be true because it's false only when P is true and Q is false. P if and only if Q is true because PQ have the same truth value in here. In the second row, when P is true and Q is false, then negation of P will be false. P and Q will be false because both P and Q must be true for the and to be true. But P or Q is true because P is true here, and P implies Q is true. I mean, that's false, I'm sorry. That's exactly the case when, the only case when the implication or conditional statement is false. P true, Q false, okay. And P if and only if Q is also false because P and Q have different truth values. The next row is P is false and true, Q is true. So negation of P is true this time. P and Q is false again because P is false, and the P or Q is true because T is true. P implies Q is true because P is false. Whenever P is false, this is always true. And P, even only if Q is false, because P and Q have different truth values. The last row, both P and Q are false. Negation of P is truth. P and Q is false. P or Q is false. P implies Q is true. Whenever P is false, then it really doesn't matter. P implies Q will always be true. Will always be true. P if and only if Q is truth because P and Q have the same truth value. And they are equivalent logically. Okay. So this table gives the truth values of common compound statements we already discussed. Any questions so far? Okay. The next thing is called compound statement. Well, we already talked about the compound statement, but this is a formal definition here. We already saw, 5 types of compound statements here. But the formal definition is here. A compound statement is a statement that has been built by applying at least one logic connective to one or more statements. So you can have more than one logic connective, or more than one statements. Previously, we just talked about one logical collective and maybe one or two statements, but you can have more than those in both. Okay. So for example, the PQ, R, and SB statements. So there are 4 statements in here. Then you can make a statement like this, pretty complicated. And it is still one statement. It is a compound statement. Okay. So you have and implication or negation, implication here and in here again. So we have 1, 2, 3, 4 logic connectives and 4 statements. But as a whole, it still make one compound statement. Okay. And we call PQR and S the components of the compound statements. Okay. So each individual statement in this expression is called the component. We're going to stop here and continue the topic next time. Any questions so far? If not, let's just stop it here. Okay, everything looks good so far.